So in this example, in example 11, we are only actually going to practice finding a particular integral for this particular function. So this is what they give you, different possible right hand sides, so the values for f of x, functions of x, that f of x is. So a constant, a function of x, x squared, e to the power of x, and 13 sine 3x. So we'll go through different scenarios using our method. So we're not about finding the complementary function, which is just the solution to the left hand side, because you've already practiced it before. So let's find the first one. To find the particular integral that you then add to the complementary function is to consider what the particular integral could be. So if f of x is equal to 3, we're going to try the particular integral of y is equal to k. The next step is to find the differentiated y, particular integral, once and twice. So the first one is going to be 0, and the second one is 0. So that's the first step you do. So first, differentiate the particular integral you are considering to get y double dash and y dash. Now the second thing is to substitute y dash and y double dash into the equation you are solving. So here, that's what we're going to do. So we're going to substitute these into the equation we are solving. And the equation we are solving, this equals to 3. So the first one is the second derivative, which is 0. The second one is the first derivative, which is 0. And the last one is 6 times k, sorry. Y is k. And that's equal to 3. So that allows us to find the value of k. 6k is equal to 3, so k is equal to a half. There you go. So what is the general solution? Remember, it's complementary function plus particular integral. So in our case, it's whatever the complementary function would be that we would find, plus our particular integral, which is a half of, There you go, because that's the particular integral. So now let's have a look at the second type. So what if it's equal to 2x? So if f of x is equal to 2x, then we are going to try the particular integral to be y equals ax plus b. So we must try a linear function. So we're going to differentiate it once to get a, and differentiate again to obtain 0. Now sub into the equation. So the second derivative is, let me just copy the equation. That's minus 5y dash. It's perfectly fine to use dashes, is equal to 2x. So that's our equation. So we're going to put 0 minus 5a plus 6 times ax plus b. And that's equal to 2x. Now we have to use this as a, well, it looks like one equation. We've got enough to find the values of a and b, because whatever is on the left hand side must be equal to the right hand side. So on the left hand side you have got, if you multiply it out, we've got 6ax plus 6b minus 5a, and that must be equal to 2x. So if you look at it, how many x's have we got? 6a, so they must be equal to 2. So 6a is equal to 2. How many constant terms have we got on the left hand side? 6b minus 5a. How many on the right hand side? none, so that's equal to 0. So from the first one, we got a is equal to 1/3. From the second one, 6b is equal to 5 times 1/3. So b is equal to 5/3 divided by 6, which is 5/18. So the particular integral is going to be y equals, remember we were trying this one to be our particular integral, so that becomes 1/3 of x plus 5/18. If you were writing general solution, you would have to find the solution to the left hand side auxiliary equation, and you'll call it complementary function, fill it in here, and then follow it by a particular integral. There you go. Let's have a look at the next one. So when it's 3x squared, so what happens there? Just get a piece of paper. There you go. So using this idea, let me just write down the equation we are solving in a shorthand way, which is perfectly good way of writing it. This time it's equal to 3x squared. So for the work on the particular integral, which very often I do on the right hand side, we're going to try y equals, since it's a quadratic, we're going to write the full quadratic, ax squared plus bx plus c, differentiate it once to obtain 2ax plus b, obtain the second derivative, 2a. Now substitute, so now sub, going to obtain 2a minus 5 times the first derivative, 2ax plus b, plus 6 times ax squared plus bx plus c, and that must be equal to 3x squared. And now we're just going to find the values of a and b by comparing the numbers of x squared on the left hand side with the number of x squared on the right hand side. So we're going to compare how many x squared we have. You don't need to multiply everything out. You could see that on this side I've got 6a, and on the right hand side I've got 3. That's not enough to find a and b. I can find a from that. Well, let's compare the x's. So here I've got minus 5 times 2a, so minus 10a. By all means expand it first. 6b plus 6b, and that's equal to 0. That should be enough information. You can use the constant term to check whether we are right. So a is equal to 1/2, 6b is equal to 10a, and that's equal to 5, so b is equal to 5/6. We could check by comparing the constant terms. So you've got 2a minus 5b. Oh, I've got to find c. Of course, we need to do that anyway. Daft thing to say. Okay, so that will be enough to find c. So it's 5b minus 2a. 5b is going to be 5 times 5/6, which is 25/6, and 1/2 of 1/2, so it's 25/6 minus, times it by 3, there you go. So that's what 6c is. So c is equal to 19/36. So the particular integral for this f of x equals to 3x squared will be a is 1/2, so it's 1/2 x squared, b is 5/6, so 5/6x, and c is 19/36. So that would be particular integral, and general solution would be whatever the complementary function is plus the right hand side of that particular integral added on to the complementary function. So there you go. So we have got, this was example 11c. So let's just double check 11c, and then we've got to find e to the power of x. So again, let's jot down the actual equation we are solving. This time is e to the power of x. So particular integral, let it be y equals to k e to the power of x. Okay, so I need to be very careful with these functions and the next ones. Sometimes they won't work, but we'll discover it in a moment. Okay, so no change whatsoever in the look of things. So we're going to substitute this into the equation. There you go. Now, if you look at this very carefully, you will have k. You can compare how many e to the power of x is. So you've got k minus 5k plus 6k is equal to 1 lots of k. So that gives me 6, 7, 2k is equal to 1 lots of, so 1 is k is equal to a half. So the particular integral here is y is equal to a half e to the power of x. Good. And then we've got the last one. So that is part e. So y double dash minus 5y dash plus 6y is equal to 13 sine 3x. So over here, when you've got a trig function, you have to consider particular integral to be a combination of sine and cos. So you just don't have a choice. So we could put p cos 3x plus q sine 3x. And to differentiate it once, minus 3p sine 3x plus 3q cos 3x. Differentiate it again, so it's minus 9p cos 3x and minus 9q sine 3x. Substitute it into the left hand side of the equation, so you have minus 9p cos 3x minus 9q sine 3x. Minus 5 lots of the first derivative, so it's minus 3p sine 3x 6 times p cos 3x plus q sine 3x, and that's going to be equal to 13 sine 3x. Okay, so that's enough for us to compare the number of sine x's and cos x's on both sides. So let's look at cos x's. So it's minus 9p, then we have minus 5 times 3q, so minus 15q, and then 6 times p plus 6p. That will give me 0 on the right hand side. Sine 3x's, so I will have the rest of them, so minus 9q, then minus 5 times minus, so it's plus 15p, and then 6 times q plus 6q on the left hand side, and there's 13 on the right hand side. Let's just tidy this up. So that's going to be 3p is equal to 15q, gives me p is equal to 5q, and this one is minus 3q plus 15p is equal to 13. So if I substitute 5q here, that gives minus 3q plus 75q is equal to 13. So 72q is 13, giving me q is 13 over 72. That doesn't look good. Let me just double check what I've done wrong here. Minus 9 plus 15 plus 6, that's correct. Let me just put the top one. -9 minus 15 plus 6. Okay, that's all correct. So let me just double check this one. 15. Oh, okay, so that was minus. Maybe that's where I made a mistake. So that minus is equal to 15, so that's minus 5. So that should be minus, and that gives me 70. Just double check. 13 divided by 78, 1/6. So that's minus, giving me Q is equal to minus 1/6. So P will be 5/6. That's better. Okay, so that means the particular integral for this equation is going to be A equals, remember the particular integral we were considering is this one. So it's 5/6 cos 3x minus 1/6 sine 3x. There you go. So now you can have a go at, no, we're going to stop. Okay, so let's have a look at the whole procedure method of solving differential equations of order 2. So the differential equations of order 2 will normally look like this. So you will have a combination of the second derivative, first derivative, and the function of y on the left hand side. On the right hand side there will be a function of x there. And then to get the general solution, you'll have to find what's called complementary function. Complementary function is the solution to the homogeneous equation you obtain by making the left-hand side equal to 0. So this is where you're going to find the auxiliary quadratic and check what the roots are. And if there are two distinct real roots, the solution is of one type. If the discriminant is 0 and there is a repeated root, the solution looks a little bit differently. And if there are complex roots, then you will have differently looking solutions. So you'll need to memorize those 3 types. Then the next step is to find the particular integral, which is going to be dependent on what's on the right hand side of the original equation. So if it's a constant term, you will try particular integral to be constant, k. If it's a linear combination on the right hand side, then you will try particular integral of a linear form, ax plus b. If it's a quadratic, then you will try ax squared plus bx plus c as your particular integral. And then of course you could have trig function or exponential function. You shouldn't have anything else. And then you'll try particular integral to be, if it's a trig function, it's going to be the sum of trig combination of sines and causes as your particular integral. If it's exponential, you try that exponential k times e to the power of whatever the kx it is. So there will be some exemptions, and we'll look at those situations in a moment. So then once you find the complementary function and the particular integral, you add them together and you write y equals the sum of these two, and it's going to be the general solution. So that's the process. So I think we've done this example. Oh no, we have found the solutions to the we have found the particular integrals. So all we need to do is now put the particular integrals together with the complementary function and state the solution, the general solution. So let's just remind ourselves of how to find the solution to the homogeneous equations, which is y double dash minus 5 y dash plus 6y equals to 0. So you write it in the auxiliary quadratic form, and that then you solve it, which is -2 and -3, giving us the roots, two distinct roots, 2 and 3. So the complementary function for this particular equation is the solution to this homogeneous equation. So it's y equals, it's going to be a e to the power of 2x, because 2 is the root, plus b e to the power of 3x, and that's the other root. So remember, this is a e to the power of alpha x plus b e to the power of beta x. So that's the form it normally takes. So now we just need to look up from example 11 what was the particular integral for that example. So we had it as y equals to a half, k was a half. So then the general solution for part A is going to be y equals a e to the power of 2x plus b e to the power of 3x, that's your complementary function, plus a half. There you go. For the second general solution, it also is going to be y equals e to the power of 2x plus b e to the power of 3x, and just need to remind ourselves what the particular integral was in example 11b, and that was y equals to a third of x plus 5/18. So all you need to do is add that, a third of x plus 5/18. Okay, the next one was also a general solution. We'll have y equals a e to the power of 2x plus b e to the power of 3x. And if you remember, the particular integral was a quadratic function. It was a half of x squared plus 5/6 of x plus 19/36. So we just need to add that to the complementary function. There you go. Okay, let's just do the part D. That was where we had e to the power of x. The particular integral that was found was a half e to the power of x. So it's a e to the power of 2x plus b e to the power of 3x plus a half of e to the power of x. And then finally, the one at the end was the complex particular integral, and it was -1/6 of sine 3x plus 5/6 of cos 3x. That gives us general solution as a e to the power of 2x plus b e to the power of 3x minus 1/6 sine 3x plus 5/6 cos 3x. So these are what we call general solutions. Still general solution because we don't know the values of a and b yet in this particular instance. Okay, so let's move on to example 13. So in the example 13, we're going to find the general solution of the following equation. So it's exactly the same equation as before on the left hand side. So let's write complementary function. That was y equals a e to the power of 2x plus b e to the power of 3x. Okay, so over here we are reminded that there are occasions where our method of finding the particular integral fails, and it will be in this particular case. So the particular integral in this case, normally when you see on the right hand side e to the power of 2x, you would want to try, let's just do particular integral on this side, you would want to try particular integral to be y equals k e to the power of 2x. and then you realize if you try to do it, it will fail. I will have a go in doing it and show you that it fails, but before I do that, I'll explain why it will fail. So it will fail because in the actual complementary function, we already have a e to the power of 2x. So we have got a constant times e to the power of 2x. So it cannot work. But let me show you that it won't work indeed, okay? Just to show you. So we'll have y dash is going to be 2k e to the power of 2x, and y double dash is equal to 4k e to the power of 2x. So substituting it into y double dash minus 5y dash plus 6y equals e to the power of 2x. Let's see what happens. So you're going to put 4k e to the power of 2x minus 5 times 2k e to the power of 2x plus 6k e to the power of 2x. That's on the left hand side. On the right hand side we have e to the power of 2x. Now if you add these together, you have 4 add 6, which is 10 minus 10, that's 0, equals to e to the power of 2x. This is absurd, okay, so it doesn't work. So in this situation, you will need to know that this will fail, or you tried it and it clearly failed. Then we're going to try a different particular integral. Okay, so let particular integral be y equals, and in that case, as it's suggested here, we'll try something k e to the power of kx. So they use lambda x e to the power of 2x. Actually, I will use k because I tend to use k a lot. Okay, so let's differentiate it first, because we need to find the first and second derivative and then substitute it into the equation. So this is clearly the product rule, u and v. So we're going to differentiate u, which gives us k multiplied by v. And then the other way around, so kx multiplied by 2e to the power of 2x. So that gives me k e to the power of 2x plus 2kx e to the power of 2x. There you go. Let's do the second derivative. So differentiate the first part, which is 2k e to the power of 2x, plus the derivative of the second part. But we've already differentiated kx e to the power of 2x. So when you differentiate this, it's just going to give us two answers of this differential. So it's going to be 2 times k e to the power of 2x plus 2kx e to the power of 2x. So let's just tidy it up slightly. You'll have 2ke and 2ke, that's 4ke to the power of 2x, plus 2 times 2, which is 4k to the power of 2x. Now we've got the first derivative, we've got the second derivative. We're going to take these and the function y and substitute the 3 into the original equation. So substituting, we're going to obtain, so into y double dash minus 5y dash plus 6y equals e to the power of 2x. So into the left hand side goes the second derivative, which is 4k e to the power of 2x plus 4k e to the power of 2. I've lost an x here, let me just double check. Oh, it was x. Okay, so that's the second derivative. Then minus 5 lots of k e to the power of 2x plus 2kx e to the power of 2x plus 6kx e to the power of 2x, and on the right side we've got e to the power of 2x. So let's just now add them together. You've got 4k e to the power of 2x minus 5k e to the power of 2x, so that gives me minus k e to the power of 2x. Now the others should cancel. Let me just slowly do that. 4k e to the power of 2x, that's this part. Then you've got minus 5 times 2, so minus 10. So I keep forgetting writing kx. Kx e to the power of 2x, and then plus 6kx e to the power of 2x. And on the right hand side we have e to the power of 2x. And as you can see, these 3 cancel. They must cancel because we haven't got any terms involving these on that side. So that gives me minus k must be equal to 1. So k equals to minus 1. So now for general solution, we need to take the complementary function plus particular integral y equals to that. So it's a common mistake is to forget to write y equals, so don't forget it. So a e to the power of 2x plus b e to the power of 3x, which is the complementary function from over here. And then we've got particular integral, which is y equals to minus 1 x e to the power of 2x. So it's minus x e to the power of 2x. And that is the general solution. Perfect. Okay, so we've got one more example, and then you'll be able to have a go at exercise 7c. Okay, so over here we've got to find the general solution to the differential equation, and we've got a totally different equation. So let's look for complementary function first. So we've got y double dash minus 2y dash. Let's just do that. It's solution to this homogeneous equation. So m squared minus 2m is equal to 0. So it's m minus 2. So we've got two solutions. So the solution, two different complex solutions, a e to the power of 0x plus b e to the power of 2x. But that is just a plus b e to the power of 2x. Okay, again over here you'll see that this, if you use particular integral when you go for searching for the particular integral and you use constant, it will fail. So particular integral y equals k will fail because we already have a constant being part of the complementary function. So over here, yeah, we can, again, like in the example before, we could try it and you can just fail and see that it won't work. So what you need to do, you need to try a different combination. So no point just trying constant. So you can pretend, well, you can try a linear equation, or you can try a quadratic equation. Both would work, but let's just go for linear first. So we're going to try the particular integral y equals to ax plus b and see if it works. So y dash is a and y double dash is 0. So substituting these into the y double dash minus 2y dash equals 3. So it's 0 minus 2a is equal to 3. So that gives me minus 2a is equal to 3, so a is equal to minus 3 over 2. Okay, so I think in that particular case, what we are going to have is, oh, I know what I've done. Okay, no need to try the b here, because that's why we couldn't find it, because b is a constant, and we already have got constant in the general solution. So even if you did leave the constant as being a particular integral, so if you left it there, and your particular integral would be then y equals minus 3 over 2x plus b, and then general solution can be the complementary function plus particular integral. So y equals to the complementary function, which is a plus b e to the power of 2x minus particular integral. So as you can see, these two, they can be rewritten altogether as a constant. These two form a constant. So you can then combine them into a constant, let's say, I don't know, let's call it c plus b e to the power of 2x minus 3 over 2x. There you go. And even if you left it like this, that would work. Okay. So now you can have a go and complete all questions in exercise 7C.